one thing before we actually start the examples here, so we're going to do some examples in worksheet 5. But like I said, one thing that I want to do and make sure you understand before we do these examples is this. If we were to write the integral, let's say, from 1 to 2 of the cosine of x dx, then we would take the sine of x and evaluate that from 1 to 2. Okay, because the derivative of the sine of x is the cosine of x. Okay, where you learned that. I mean, you learned how to evaluate a definite integral, and we learned that you can take any antiderivative of this integrand and use it to evaluate it at the upper and lower limits of integration. We have not really mentioned that, by the way, there's this sine of x plus any constant. Sine of x plus 2 is also the cosine of x. So the derivative of sine of x plus any constant is the cosine of x. Why would we choose sine of x when we're evaluating definite integrals? Because the sine of x is the easiest of them all. And if we chose sine of x plus 2, the definite integral would have the same value. So you can try that on your own if you want. But we choose the most simple antiderivative. But the thing to keep in mind is that an antiderivative, I'm trying to find if there's one on this page. An antiderivative in general of the cosine of x dx is equal to the sine of x plus some constant. And in integration, we use the capital C to represent that constant. Okay, so that's where that C is going to come from. Find C. Okay, in these examples, I didn't want you to get I didn't want you to feel like, wow, where'd that C come from? So I wanted to explain that a little bit. So hopefully that helps. And here's our first example, and I'm going to show you two methods with which to find the answer that we're looking for. We're given that the derivative of y, so we're given the actual y prime, the rate of change of y, and we're given that we have one initial condition. So here's the derivative, but here's an initial condition of the function y at 2 is -1, and we're supposed to find the value of the function y at x equals 3. Okay, so that's our goal. One method for finding that would be to actually find this integral by antidifferentiation and use the initial condition to find c. Okay, so you can look this over. This is not the way we're going to solve most of these. Okay, but when the antiderivative is pretty easy, in other words, if y is equal to this integral, then y is equal to the antiderivative of 3x squared is x cubed. Okay, 3x cubed over 3. And then the antiderivative of 4x is 2x squared. Antiderivative of -5 is -5x. And then we have this plus some constant. Okay, and then the initial condition that when y is equal to, or sorry, when x is equal to 2, way back up here, so when we put a 2 in for x, we would get a -1 out for y, and then you just have this one variable c, and by doing a little bit of math here, you get that c is equal to -7, and so you get the initial function y, a specific function y, I should say, and then once you get that specific function y, you'd plug in your 3 and for x, and you'd get an output, and the output when x is equal to 3 is 23. Okay, so I ran through that kind of fast. We're going to cover this more in chapter 6, but like I said, this is not the way we're going to do most of these problems. The way we're going to do these problems is by using the fundamental theorem of calculus, okay, because that's the section we're in, and this is the most convenient method, especially when you get to use your calculator, which you're going to be using sometime soon. Okay, well, remember that the initial condition was that we knew what y was when x was 2. Okay, then our unknown is what the y is when x is 3. Okay, so those are our limits of integration. You put your initial condition here, and this is of the utmost importance. Initial condition here. Okay, that's the input. Okay, and this is our unknown. So we always put our unknown input in place of the upper limit of integration. Okay, and we know that when y, remember this right here, the integrand, this is a rate of change. The antiderivative of y prime would be y. Okay, or you have y, and then you have y prime, and then you have y double prime. We're not talking about y double prime though, but when you want to integrate y prime, you evaluate the upper limit of integration at the antiderivative of y prime, and the antiderivative of y prime is y. So we have y of 3 minus y of 2. Well, again, y of 3 is what we're looking for. Y of 2, we were given. Okay, we were given that y of 2 is negative 1. Okay, so we subtract negative 1, and anyway, when we're subtracting negative 1, we're really adding 1, which means we subtract 1 from both sides, and nevertheless, we get a negative 1 plus the integral from 2 to 3, and that's y of 3. Okay, well, y of 3, when you evaluate this integral, this definite integral, you're going to get 24. And on the back, where is it? Okay, so y of 3 is negative 1 plus, and this is you evaluating the definite integral. And actually, in this case, method 2 was a little bit longer. Okay, and something to keep in mind that we got 23, both methods. Okay, and then if a closed form, I'm going to explain this. If a closed form of the antiderivative exists, either method may be used, and sometimes, as you saw here, method 1 actually does turn out to be a little bit less work. And a closed form would be when we have a simple antiderivative. In other words, if it's like cosine of x, we know what the antiderivative of the cosine of x is. Sometimes we get things like this, where f prime is the sine of x squared, and we don't have an antiderivative of the sine of x squared that we know of, and so the way we would do a problem like that is by using the fundamental theorem of calculus. You can't use the method 1 for problems like this. Okay, so problems like this, here we go. This is an easier one now because we get to use our calculator. Okay, so notice that example 2 says that the rate at which f is changing, so f prime is sine of x squared. Okay, f of 2, given an initial condition when x is equal to 2, and notice, oh, interesting. Well, yeah, I guess it doesn't really matter where you put the 2. I would put the 2 on the bottom, just because I always put the initial condition on the bottom. You don't have to. But notice that they put the 2 on top here, and the input that we are saying, well, that's the unknown, that goes on the bottom. I guess when you have an unknown that's smaller than the input, then put it on the bottom. It doesn't really matter. It's still going to end up to be the same thing. You're still going to get the same answer. So the integral of the rate of change is the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. We're already given that this guy right here, f of 2, we already given that that's 5, or sorry, negative 5. Okay, and if that's negative 5, then we're going to, actually what they did was they added f of 1 to both sides, so you get f1 by itself, and then subtracted the integral. Okay, but again, the f of 2 has a value of negative 5, and then when you subtract this integral, which this integral you'll use your calculator. So negative 5 minus this value here on the calculator, you'd get negative 5.495. Okay? Alright. Piece of cake? That's example 2. Let's look at example 3 and see what we've got. This is ending up to be a pretty long lesson, isn't it? You're probably already saying that. Worksheet 5. Applying. Okay. So why don't I do this? Let's just do this one example, and then I'll let you do some of those examples on the worksheet 5. Okay. Alright. So we have the graph of f prime, and more than likely what we're going to be doing here is we're going to be finding the areas under these regions here. That's always how they go. So let's find those areas first. 2 times 1, 2, 3, 4. 2 times 4 is 8. Half of 8 is 4. So this is a 4. and we have a semicircle over here. It has a radius of 2, and we know that pi r squared, pi times 2 squared, is the area of a circle, so 4 pi is the area of the circle, but we have to cut that in half, and we get 2 pi as the area below the curve. Okay? So therefore, it's saying if this is the graph of f prime from negative 2 to 6, we're given that f of negative 2 is 5. Okay? So if f of negative 2 is 5, then we're trying to find f of 0. Then we would go from negative 2 to 0 of f prime of x dx. I should have put the parentheses around there. So if we want to find f of 0, then we're going to integrate from negative 2 to 0 because we were given the initial condition when x is equal to negative 2. And what is that? That is f at the f meaning the antiderivative of f prime, f at 0 minus f of negative 2. Okay? Well, like I said, we're trying to find f of 0. Let's add f of negative 2 to both sides. Okay, f of negative 2. Okay, and when we add f of negative 2 to both sides, we get f of 0 is equal to, that's what we have over here. F of 0 equals f of negative 2 plus this integral. Okay, well again, the f of negative 2 is 5. And the integral from negative 2 to 0 would just be 4. Okay, and that's what we got. So that's the way I would do it. I would go 5 plus 4, and I get 9. Okay, so when I already show my areas here, I don't have to go through this again, because then I get some calculations here where I'm trying to keep things simple, and if you go from negative 2 to 0, you get 4. Okay, well, f of 2, that would be, when we want to find f of 2, then what would I do? Well, I would say, well, from negative 2 to 2 of f prime of x dx is lowercase f of 2 minus lowercase f of negative 2. And what are we trying to find? We're trying to find f of 2. So we add f of negative 2 to both sides, and we get this guy right up here. F of 2, okay, that's right there. And we get f of negative 2 plus the integral from negative 2 to 2. Well, negative 2 to 2 is 8. 5 plus 8 is 13. Okay, so we have the f of negative 2 is 5. This guy is 8, and 5 plus 8 is 13. Okay, and then f of 6, you can obtain that the same way. So I guess we can do examples 4 and 5 in class if you need me to walk you through those examples. I'll let you look at those on your own. But what I would like you to do before you come into class, so that's like 45 minutes worth of work that we just did. Okay, we really want to make sure you're understanding things here. So you are allowed to use your calculator on these, and I want you to do the first let's see here, what should we do? Let's do the first how about this? How about we do all of the odd numbers? Okay, we'll do all the odd numbers for homework, and then we can do the even numbers in class. We can go over these, and then we can be completely done with the fundamental theorem of calculus in terms of a solid understanding of how to use the fundamental theorem of calculus to answer the questions in all the different forms you're going to see questions for. So here we go. You do that. I'll see you in class, and good job hanging in there.